The largest allowable stresses in the cast iron length are 30 megapascal in tension and 120 megapascal in compression. Determine the largest force P that can be applied to the length. And I've given you a bunch of the properties already, the area, the location of the centroid, and the moment of inertia. So what we have is this is our weird little link here. Here's section AA taking right there. So we've got a T-shaped link here in the middle of things. So how do we go about solving this? Same as before, we're going to determine the equivalent centric load and bending moment. We're going to superimpose those two stresses on each other to find the complete state of stress between the centric load and the bending load. We're going to evaluate the critical loads for the applicable tensile and compressive stress. And so the largest allowable load will be the smallest of those two critical loads. And I keep using that term critical. What does that mean? Critical load is the load where everything's going to fail. That's terminology that we end up seeing a lot, especially when we deal with columns. So let's move on and let's take a look at the first thing. We have to calculate out what the load is. But we're trying to find that critical load, so we're just going to say P is that centric load. I'm trying to find that, so we really have nothing to write here. And, well, we know that the moment is going to be P times D, where D is the distance of the offset. And so we can look here. Let me bring it back to the other one here. So we're applying the load right along D. And as we can see here, D is 10 millimeters off of the base of our cross-section. And our centroid is here at Y bar at C. So we need to calculate out what our D is, and so D is going to be the distance of that centroid, which is given to the problem as 0.038 meter. And then we're going to subtract from that the 10 millimeters from where we're applying the load. And that's going to give us a D of 0.028 meter. And so that will tell us that our moment is going to be 0.28 meter times P. Because once again, we're trying to find P. And so we're going to superimpose those two forces on each other. Now, if you look back to the original problem, this is all compressive, so we're pushing down. So as we're pushing down, as we're being compressive here, that's going to cause a bend. And that's going to bend it like that. So this will be on A is going to be our tensile stress, and at B is going to be our compressive from the bending. From the axial, it's all going to be compressive stress. So let's take a look at our stress of A first. It's going to be negative P divided by A plus MC, and we'll use A for the distance from the neutral axis to A divided by I. And so if we plug that in, we've got negative P divided by 3e to the negative 3 plus 0.28p, which is our moment, times our distance from the centroid to there, which is going to be 0.022 meter, divided by I, given the problem 868, times 10 to the negative 9th. And so that tells us the stress at A is going to be a positive 377 times P. And so, sorry, let's look at our stress at B. And stress at B, this is going to be our compressive stress. Negative PA minus MCB over I. Once again, we're just going to plug all of our numbers in, and then we're going to end up with a expression in terms of P, 0.28P times, and that is also, sorry, I'm just looking up here, CB is going to be 0.038 meter. And we just, how did we get those? We just did a little bit of math. And the math for this one is easy because our centroid is measured from the bottom. And where did the 22 come from? We just took 60 and we minused that 0.38 to give us that. So let's just put that down. There's CB, there's CA. and then divide that by 868 e to the negative ninth, and so our stress at B is going to be negative 1559 times P. So those are our intermediary points. So we've set up P, so now we'll evaluate them at our critical loads. So if we look at it for tension, the problem told us that our maximum tension is going to be, so stress max in tension is 30 megapascal. So we'll go to our stress of A, which is our tension. And so stress of A is 30 megapascal, and that's going to equal 377 times P. So if we solve that to get a 30 megapascal tensile force, 79.6 kilonewtons is what's going to give us that. So now if we look at our maximum stress in the compressive side, the problem stated that we have 120 megapascals. So stress of B is going to be 120 megapascals, and our problem stated that we've got negative 1559 P. Oh, and since this is compressive, this has to be a negative 120 megapascals, so compressive stress. And so what that's going to give us, if we solve for P, that load is going to be 77.0 kilonewtons. And so we look at these two numbers, the largest allowable load is going to be that 77 kilonewtons. So why is it the 77 instead of the 79? And that was the wrong thing. I meant to grab the highlighter. There we go. So why is it 77? Because by what the problem says, as soon as I hit 77, it fails the compressive test. I can't get to the tensile test because it's already failed the compressive test. So I'll never be able to get it to 79.6 because it already fails at 77. So the largest load that I can place into this link will be 77 kilonewtons of force.